Okay, here's another chain rule example where we have a 2x plus 5 linear function trapped inside of a cubing function. So expanding out a 2x plus 5 cubed is not a lot of work, but it might be the first time where the chain rule will be more efficient than simply expanding out our composite function here. So let's do that. Let's just do our chain rule. So y prime is going to be, now we have to differentiate the outer function first, which is the same as differentiating x cubed. Our 3 comes down in front, and of course our exponent now is 3 minus 1. And don't forget, your trapped function has to stay inside there. So your inside function is still trapped. And now to finish off our chain rule, we're chaining together another derivative, and we're multiplying these two derivatives, multiplying that by the derivative of that trapped function, which is 2x plus 5. Of course, this just produces a 2, and we could probably skip this step, but let's write it out. So we have a 3 multiplied by 2x plus 5 to the power of 2 multiplied by just a 2, because the derivative of 2x, of course, is 2, and the derivative of 5 is 0. So this gives us our derivative, which is 2 times 3. Again, 2 examples in a row, we've had a coefficient of 6, which is just kind of coincidental. And here I wouldn't bother expanding all that out, because here's our derivative. And remember, if we simply want some tangent slopes, we can just plug in x's into this version as opposed to the expanded version. Okay, so there's our chain rule. And if you want some extra practice, you could expand that out and, of course, use your power rule, but then you'd have to do some factoring to get it back to this form. So let's abandon that strategy and start to get used to working with the more efficient chain rule in this case. And also what we have to get used to is notating our composite function and being clear with different ways that we can represent the chain rule using different calculus notations. So let's look at our y equals 2x plus 5 all cubed. Now hopefully it is obvious that our inside function was 2x plus 5. So I'm going to say that is my trapped function, which I will call g of x, 2x plus 5. And our outer function was just cubing, the cubing function, or just the power function, x cubed. Now, of course, what we have above here is a composite function, which, if you remember from first semester, this is f of g of x, which simply means g of x is trapped inside our f of x. So another, I guess, couple of ways we can write the chain rule, but since I'm opting for function notation here, if we do have a derivative, I guess in white works, if I have a function that is a composite function, and I think I'll write it in the more familiar bracketed version here, f of g of x, the derivative of that function is going to be the derivative of the outer with the trapped function inside, multiplied by the derivative of the inner function. So I'm not sure if that's helpful, but that is a common way you will see the chain rule written in function notation in your textbooks. So maybe just to illustrate that with the function notation approach, that if you recognize you have a composite function, that you surely would have if you've gotten this far, we would differentiate f of x, which maybe we'll do that in green this time, which is 3 comes down, the original power drops by 1 to a 2. And don't forget, our g of x has to be trapped inside still, 2x plus 5. And then we're going to multiply that by, I guess still in pink, the derivative of g of x, which is just going to be the derivative of 2x plus 5. And of course, we get the same answer and pretty much the same approach. I guess I'm just trying to demystify common ways the chain rule is written, again, in your calculus textbook.